All right, using diagram, explain how atomic line spectra works. All right, so you could use lots of different diagrams, but I'm going to do this.
It's a firework.
All right, so here's a boron atom. I know that it says it has 5 electrons in it. I do something like add heat to it, and we'll say that this electron here jumps up to this energy level. And so now this atom's electrons are not in ground state. And when this electron goes and falls back down to where it came from, it produces light. And that's a line spectra. So depending on how many of these electrons jump up and how many orbitals they hit and fall back down from, you'll get separate lines. And this will encompass for visible spectrum, it'll encompass the entire rainbow. So you'll only see a few colors, few line colors instead of the entire thing because we're only looking at one atom. I totally failed to mention something on Tuesday that is super interesting. Do you guys know where helium gets its name from?
No,
or does it sound like it gets its name from?
Helium.
The sun. Yeah, it actually tells you on the periodic table. It says
like helium.
Etymology is etymology is Helios. And so the reason that it got named after the sun is we had found basically all the known elements, didn't know we hadn't found helium. Looked at the line spectra and basically took, so let's say that this is the line spectra that I do right here. This is the one for boron. And so then they took the one for all the other elements and they laid them over the top of each other with transparencies. And we got basically it looked like a rainbow with gaps in between. And they said, well, let's compare this to what comes from the sun. And so then they did the spectroscopy on the entire sun and got all of the lines and realized they're missing some lines. And so when they realized there are line spectra in here that we don't have an element to associate with it, they decided there must be another element and we don't know what it is. And this is its line spectra. So they postulated that, hey, since we haven't found it, it must be a noble gas. And so they just distilled air more carefully and then they found helium. Okay, so let's fill in the missing pieces from this one. So I've got this polonium, and what do I want to, what should I do with the superscript number?
Subtract 4 from it.
Okay, so this is a 210 up here. And my subscript number?
Subtract 80 or subtract 2 from 84.
And we end up with, we go with that?
Oh, it's a lot easier than I thought it was.
Okay.
So what is the A an alpha particle?
It's actually a poor font. I should have picked a different one. It's that. That's the symbol. That's the lowercase Greek letter alpha. Okay. Do you want me to try to do a better job?
So, but it's okay.
They're all gonna suck.
Really, it's okay. But is it still representative of the alpha particle?
Yeah. So you can either write it like this: 4 to terrible alpha, or 4 to He, or what? If you're gonna write the He part, you technically should write 4 to He plus 2. Because this is an alpha particle, so it's 2 protons, 2 neutrons. It doesn't have any electrons yet. But when this thing comes out of the nucleus, what do you think it does the moment it runs into something? We're talking about a helium atom that doesn't have any electrons.
Then it'll steal some electrons.
It from anything in the universe. Doesn't matter
Yeah.
what it is. It will take the electrons away from that thing.
Also, what or not what, but can we have on the right side of these nuclear equations? Can we have alpha and beta particles?
No. I'm not saying that you can have a source emit alpha, beta, gamma, neutrons, electrons. You can do everything. But each one of those is individual different reactions. So if I'm radioactive and I undergo a decay, I don't have to decay the same way every time. Does that make sense?
Yeah.
I usually do, but there are definitely other modes of decay than set. And we'll probably, yeah, I'm pretty sure we'll talk about that today. Yeah, I know we will.
And then what does the N represent?
Neutron. So why should you know that's neutron?
Because there's another one on the other side?
No.
It's in the top number, which is neutrons.
Well, it's got a mass of 1, right? It has a mass of 1,
Okay.
and it has a charge of 0. So what has no protons but a mass of 1? The only answer to that is a neutron. Okay, so what's the superscript I'm missing here for the second one?
So 235, 236 minus 90, minus 91.
Nope. Close. But let's make the mistake now instead of on the test. It's not 91 so far on the right-hand side. What is it?
Is it just 90 or is it just 1?
Nope. It's 93. Kalina's right. 93.
Oh!
Because this is saying that there are 3 of those things. So this whole thing has a mass of 3. So then it's 3 plus 90. So on this side over here, I already have a mass of 93, and I need to get to a mass of 236. We okay with that?
Okay.
All right, so then we're at 143.
43.
And then what do we do with the denominator or the subscript?
Subtract 38 from 92.
Yeah.
Hold on.
So just because everything else is a 0, I'm just going to subtract strontium's 38 away from uranium's 92, and what do we get?
92 minus 38 is 54.
Which is?
I don't have my periodic table.
That's horrifying. Not having your periodic table.
I have it now.
This reaction is actually, I mean, we're not going to talk about that, but this reaction would frustrate. It would just basically piss people off that worked in my department on the aircraft carrier, because this reaction right here could cause us to have to stay on the boat after we docked because of the stupid xenon. But we won't talk about it because it's
Mr.
complicated.
Kovacic, for you, I will tape my periodic table to the office wall.
Okay,
So I will always have it.
that's excellent. You should get a shirt and just start wearing it around.
Yeah. During the chem lecture.
Written upside down so you can just look straight down.
Perfect.
Okay, so what about this? What evidence leads us to believe that light is both a wave and a particle?
So light is a wave because hold on. Oh, because refraction. I remember whenever it passes through something of different densities, it bends. And it also experiences interference.
So light undergoes refraction, so that makes it act like a wave. Light undergoes interference, which makes it act like a wave. So light is a wave when it wants to be a wave. And then what about light being a particle?
When it experiences interference, it isn't additive in energy.
Okay, is there Is there another way we can say that?
There's no constructive interference.
How about we take what
Yeah.
Ethan said and say, and we can just say photons.
Yeah.
We have to add that second part to this about the at the point of absorption because, I mean, obviously that big red light that we were talking about that was heating that giant chunk of ham or whatever the heck it was, that just big chunk of meat, the energy is additive for the object as a whole, but not at the point of contact. So I can't add those waves to perform an atomic size function, although I can heat a big chunk of meat with it. And we could just say,
Photoelectric effect.
so that 5G news story, is that causing anybody cancer? If you read that article, the reason it's horrifying is an entire township's council is walking around with these things, and the city paid for them for these people, so they can protect their data and their brains, which are obviously already gone.
Can you explain the photoelectric effect again, really quick?
I just have to draw that spaghetti monster thing.
Well, because what I have is that light is able to move electrons to create electricity.
Okay.
Is that like pretty much it?
Except that it can only. Let me add this to this. So what I mean by this portion right here, they're not additive at the point of absorption, is one electron cannot Does that make sense?
One electron cannot absorb, but one photo.
Does that make sense?
But one photon
Period.
can is
No,
what I'm
no,
trying to-
that's it. One electron cannot absorb but one photon.
Oh, it cannot absorb but one photon. Okay, you can just say it cannot absorb anything except one photon.
But but's 3 letters.
Yeah, well, I'm not lazy like you.
But the way you said it is bad English. The way I said it is the King's English.
Okay.
So again, the important part is even though, say, two photons reach that electron at the same time, each one of them doesn't have enough energy to boost that electron to a higher energy level. But if they hit at the same time, then the electron could absorb that energy and jump up to that higher level, except they can't. They can't hit at exactly the same time. The electron cannot absorb the two photons' energy at the same time. Because what would happen if it absorbed the first photon's energy? A little bit of it.
It just jumps?
It would move. So would the other photon hit it?
No.
No. So it doesn't absorb either of their energies.
Also, what happens to the photon when it's absorbed? Does it?
It's gone. It is gone. It is energy has been
Used to jump the electron?
used to jump the electron. It has been converted to light energy into kinetic energy.
Okay, cool.
All right, so this diagram, what do we got here?
Beta particles that are negatively charged, and they're lighter than alpha particles, so they move more.
So the beta moved towards the positive, the alpha moved toward the negative, and
Gamma rays don't have any charge.
bigger because 70, I think we said 7,400 times.
Yeah. Or was it 7,200? Yeah, it was 7,200.
Okay, that's fine.
Sorry.
No worries. And then this is not charged, so it's not going to be affected by an electric field. Okay.
So what exactly is it trying to show besides the charges in the mass?
It's trying to
is
show
it
two
used-
things. One, that the radioactive material is composed of 3 different types of radiation.
Okay.
And 2, that the beta particles themselves are negatively charged, the alpha particles are positively charged, and that the alpha particles are a lot bigger, and so they don't turn as much. There isn't anything else to it.
Can we use this for anything?
Well, it fundamentally explained to us what was happening when radioactivity occurs. So
Yeah.
we've used it for a lot of stuff.
Okay.
I mean, this lead block radioactive material thing, where did we see this first term?
Mm. I don't remember.
Anybody?
I only know vaguely what we're talking about.
We're talking about this right here.
Yeah, I know what we're talking about. I don't remember what it was called or who did it.
Well, was it the gold foil experiment?
This is the gold foil experiment.
Oh.
What did Rutherford fire at the gold foil?
He fired atoms.
No,
No. He fired like negatively charged
he
atoms.
fired alpha particles.
Oh right.
Yeah.
And they're positively charged.
So, yep. So because this experiment happened, Rutherford realized, hey, I could use that as sort of like a gun. And so he did. And then, so is this important? Well, it told us that the nucleus, or that the atom has a nucleus. So yeah. Okay, any questions about any of these?
Can you scroll up really quick? Please. I think. Yep, I'm good.
Anybody else?
This was the first homework in a while in which after we are done, I completely understand it.
Well, you should not let that happen. Should never
I
have let
know.
that happen.
I know.
Okay. All right. So the next thing we want to talk about is the inverse square law of radiation and some shielding stuff. So does anybody recognize the format of that equation? Intensity, basically it's like intensity at one spot versus intensity at another, and distance is inversely squared. Where have you seen it before, Allison? It's exactly the same equation with a different, instead of there being an I, it shows something else. It's the equation for the effect of gravity on another body. So if I change the I's to G's, that's the force of gravity on an object. So you could say the distance between the Earth and the Moon and check the gravitational pull on those. And you know it changes because when the distance between the Earth and the Moon change, what happens to the planet? You get to go surfing. Or you don't get to go surfing. One of those two things. I mean, imagine this planet with no moon.
Flat ocean.
Boring,
Boring.
right? The only times there'd be waves is when there'd be storms.
Or whenever there's a wave machine.
Okay. A wave machine in the ocean? That's a really,
just like
really
just
big
like a
machine.
sticker gun.
The last year I lived in Pennsylvania, some kid drowned in a wave pool.
Well, he should have had floaties on, or shouldn't have gone in the wave pool in general.
There were like 10 lifeguards there. They didn't even notice it until they turned the wave machine off, which is now
huge crowds.
Which
in
is
those
now
things.
why, well, this was a huge wave machine. This thing was 100 yards wide and 400
Oh.
yards long. It was huge. That's why there were 10 guards there. But this kid's death is the entire reason that the wave machine turns off about every 10 minutes. So if you go to like Great Wolf Lodge, there's the wave machine's going blah blah, and all of a sudden he just dies. And then they wait for the water to go calm, and the lifeguards are looking in the pool to see if anybody's in there.
There should be just like a limited amount of people, and they shouldn't let like 12-year-olds in it.
Whatever, I don't care.
Oh, what water park was it at?
The one in Allentown, whose name I can't remember. What'd you say? Absolutely, earthquake. We'd still get tsunamis, but you wouldn't have like you go to the ocean right now. There are waves. If there was no moon, you'd only have waves during interesting events like heavy weather or earthquakes and whatnot. All right, so how does this work? If there's a radiation source, what's your best method of not being irradiated?
To block yourself from it.
That's your
Second best.
second best method. What's your best
Leave
method?
Then,
Leave. Why?
so you can get distance between you and the radiation.
Yeah, look at the equation.
Distance is an important part of it.
Tell me how much more important.
10 times.
No, not 10 times.
4 times?
Not 4 times.
Squared times.
Squared. Whatever it is, it's squared. So you can't say 4 times or 10 times because you could only move 2 inches. But it's a square of 2 inches, right? So if you double your distance, what happens to the intensity of the radiation you're being exposed to? Two squared is
half.
4, so it's a quarter of what it was before. Not half, but a quarter. And this is how gravity works. If you're 100 miles from a planet, and now you move to 200 miles away from the planet, then the gravitational pull on you is a quarter of what it was when you were 100 miles away from it. You okay with that? Okay, so the most important thing is if there's radiation, just get the hell away from it. Yes, it's nice that they covered Chernobyl up with a big concrete block, but the most important thing was that basically everybody moved. So they got further and further away from it.
Yeah.
All right, so let's just do an example problem. So I've got some radiation source here, and I got a person and they're right here and they're carrying a detector, and this distance right here is, I don't know, let's say 15 meters, and at this distance this person is reading 125 millirem per hour. Okay, and so what's the new distance at the new position? Sorry, not the new distance. What's the new intensity at the new position? All right, well, I've got intensity X divided by, I don't like the X and the Y. The intensity 1, intensity 2 equals distance 2, distance 1. So what should you notice about the equation? Sorry, somebody's vacuuming. What'd you say, Kalina?
It's like a proportion between the two things.
What kind of proportion? What's the relationship between distance and intensity? It's inverse. So this is an inverse relationship, which is why the 2 is on the bottom on the left and on the top on the right. This is sort of like how Boyle's law worked. You increase the pressure, you decrease the volume. Okay, so I'm going to write, I don't know. Okay, so intensity 1, we'll say, is 125 millirem per hour. I don't know intensity 2. Distance 1 is 15 meters. What's distance 2?
Mm.
25 meters. And we got to square them. So I'm just going to rearrange this. I get intensity 2 is equal to 125 millirem per hour. And then it's 15 squared meters squared divided by 20 squared meters squared. And the squared meters cancel out. And my new intensity is what? 125 times 15 squared divided by 25 squared. 45. We okay with that? So when you do your calculation, if you get further away, make sure the number goes down. If you get closer to it, make sure the number goes up, or you're making a mistake. Okay, so the next thing I want to talk about is shielding. So I want you to read the first 2 sentences in that box there on the right that starts with the word shielding. Do you have it? Do you guys understand what the 10th thickness is? Does anybody know why they chose the amount 10th thickness?
Because we measure concrete in like inches, or we measure walls, wall thickness in
What does that have to do? It doesn't say inches anywhere up here. No. What's the metric system based off of? So I just moved decimal places, right? So with the 10 thicknesses, I just moved decimal places. So if I know that I put a 10 thickness in between me and the radiation source, what do I know happens to the intensity of the radiation on this side of the shield?
it decreases by a 10th place.
I just moved the decimal place over, and it's 1 order of magnitude less radiation than I was being exposed to without the shielding. We good with that? You
And
guys,
that's to the right, right?
well, whatever you want to say makes it smaller. The intensity is now a smaller number. So if you were being exposed to 25 millirem per hour, you put a 10 thickness of whatever it was that you needed up, then you're being exposed to 2.5. What happens if you put up 2 10th thicknesses in between you and that 25 millirem per hour source?
Would it become 0.025?
Just
Or
0.25. Yep. So it made it really easy when they said, all right, the standard would be a 10 thickness. We'll say what the 10 thicknesses are, and then you just throw up those 10 thicknesses until you drop the orders of magnitude down to a number that that's acceptable to you. Okay, so the only 10 thicknesses that I care that you remember are
Radiation pass through wood.
yes, no problem. Okay, so I'm only telling you that I care that you remember the radiation 10 thicknesses for gamma and for neutrons. Why?
Because those are the ones that pass through the easiest.
Okay. Alpha particles and beta particles can't penetrate your skin.
Wait, but that diagram shows that it can. That's a hand, right? Where are you going? I mean, I'm not saying you're right, but I'm saying the diagram is then wrong.
I always forget I can't draw with the mouse on this.
There we go.
Is that better?
Thank you.
So, do you remember when we were talking about radiation? And we were talking about the REM? And the most dangerous source of radiation is an alpha particle? So the alpha particle has a quality factor of 20. So if you're exposed to a certain amount of REM, but if you're exposed to a certain amount of Rochin of alpha particles, you have to multiply it by 20, and that tells you what your REM value is. So why am I saying I don't care if you? Why am I saying you don't have to worry about any 10 thicknesses for alpha particles if alpha particles are the most dangerous? This up here says something super specific. So I'm highlighting the exposed because an alpha particle does not expose you unless what? Exposure for an alpha particle or a beta particle only happens when you do what?
Or directly in the presence of radiation. Or
That's the only way that it can hurt you. So if somebody's standing there holding an alpha source, you shouldn't care. Your alpha source is only dangerous to you if you eat it. Right now, I'm sure there's an alpha source in at least half of your houses because half of the radiation detectors in the world have americium, and so half of them are alpha emitters. And you're not worried about that, and nor should you be worried about it unless you open up your smoke detector, scrape off the weird-looking paint, and then eat it. That is the only way it can hurt you. All right, so that
She is
sounds
having a great time.
that sounds ridiculous, right? Like, how could I ever be exposed to alpha and beta? I would never purposefully eat it. Well, that's right. You'd never purposefully eat it. So how could you be exposed to it?
It's like if there's radiation and it gets into the water.
Most important thing, she's right, is the water supply. If there is radiation in the water and you drink the water, you're not going to know it. It's just going to be in the water. Or if you eat something that absorbed water that had that radiation source in it. Those are the ways you get it. So, did you guys see the movie Book of Eli?
No.
It's the most recent movie that I saw that they used this, but somebody was offering the main character some water, and so the person was holding this jug out, and then he pulls a Geiger counter basically out of his off of his back and puts it up next to the water, and it goes crazy. No, sorry, I don't want to drink that water. So post-apocalyptic, road warrior, make sure you have a Geiger counter on you.
Yeah.
Or know somebody who's got a Geiger counter on you. I have a Geiger counter.
Of course you do, nerd.
Just saying that. Got 3 of them.
do Geiger counters take really weird batteries or something?
The only ones I have are old and they just have proprietary batteries inside of them. But they run off of 12 volts, so you could easily hook them up to a car battery.
Okay, because I have an old Geiger counter and it's got the weirdest battery slots that I had no idea. So that makes sense.
Well, I mean, anything that doesn't have a standardized battery, its battery's going to look weird. Like, what's the battery in your phone look like?
Gigantic.
Not standard.
Flat and tiny.
Alrighty. So, the reason I'm concerned about alpha and neutrons is because those are the things that have penetrating power. So, alpha particles are blocked by 2 inches of lead for their 10 thickness. The neutron is interesting. It's 10 inches, so that kind of sucks. But it can be blocked by water, or plastic, or concrete, or even fuel oil. So on the aircraft carrier, we had lots of what on our aircraft carrier?
Fuel oil?
Fuel oil to power our aircrafts. So the tanks are actually around the nuclear reactor. That might sound like a terrible idea, but doesn't matter. Someone's gonna. I mean, If something happened on the reactor that caused that stuff to catch on fire, everybody on the boat's already dead, so it doesn't matter. So, let's go back to our picture. And let's say that this is a gamma emitter, and that I not only go from 15 and back up to 25 meters. As I walk, I went through a door, and this door was 4 total inches of lead. So what's my exposure level now?
Is it a
Point.
100?
0.45 rems.
It's 0.45 millirem. So I take this decimal place that was right there, 1/10 thickness, 2 10 thicknesses, and so now my answer is 0.45 millirem per hour. So your best option is to get away from it. But if you can't get away from it, then your next best option is to shield yourself. On our ship, we were given, everybody that was in the nuke department was given this little thing. That's terrible. You know what? I wonder if I can find one. No. Okay, whatever. We had this object that we put on our belt, and it was about the size of I don't know, like a roll of quarters. No, maybe like a roll of nickels, something like that. Didn't weigh nearly as much. It was very light. Just clipped onto your belt, and we were required to wear it around with us 24/7 on the boat. And what it did was radiation would hit this thing, and then the electrons would be excited. And typically, what happens after the electrons get excited?
Energy is produced.
No, energy is absorbed. So the energy absorbed, the electrons get excited, they move up to a higher energy level, and then what do?
They fall back down.
They fall back down. In this thermoluminescent detector, if it was checked within 60 days, the radiation, those electrons would still be stuck in that higher orbital. So as you're walking around inside the reactor room, if you got hit with something, then the thermoluminescent detector, or the TLD, would get hit by it, and it would jump up to a higher level. And then at the end of the month, I would take my own TLD, and I would take it to these guys called the ELT guys, which were the radiation guys, and I would put it into the machine, and I would run the test, and I would get the number, and I would write the number down in a book. And then I would write the number, I would go write it down myself. I was in charge of the amount of radiation that I got exposed to. If somehow I got a high dose of radiation, I would be in trouble for that because I somehow allowed myself to be exposed. If I was the only person, then I'd be in trouble. If a bunch of people got hit, then we knew that there was a problem. But the most important part was I knew how much radiation I was being exposed to. So what we did one month is, when completely bored out to sea for 6 months, we took one of these TLDs and we strapped it to the flight deck in a spot that nobody would see it. And we just left it up there. And then at the end of the month, we brought it down and we read it. It was double what the average was for everybody in the reactor room. Does anybody have any idea why?
Because it didn't have any like walls.
It wasn't shielded from the sun. But
Oh.
what about me?
You are inside a lot. You're inside the boat a
A
lot.
lot? A lot is an understatement.
Did you
99.99% of the time while underway, I was 7 stories underwater. What did we just say about radiation and water?
Water can block
Block it.
radiation.
So what were me and the rest of the guys in the reactor department never exposed to?
Solar radiation.
Solar radiation. The bulk of the radiation on the planet comes from the sun. We had zero access to it. We were underwater and inside of a steel coffin. So no chances that we're going to get any radiation from the sun. So the only radiation that we got exposed to was background radiation of the materials on the boat and the reactor. And we shield the reactor so well that the Navy was confident that we wouldn't get any radiation from it that even mattered. And we proved it to ourselves. It was easy. The difference between the United States Navy and the Russian Navy is they wore TLDs, but they were never allowed to read the TLDs, never allowed to know what the TLDs said. Okay? Why?
Because they had a lot more radiation on board.
Because they were exposed to a ridiculously large amount of radiation. So why would the Soviet Navy do this to their own people?
Research?
No. Not a terrible guess.
Not to like scare them or scare away people.
No. I mean, why would they not just throw as much shielding up as we put up? They could measure it. I mean, they're perfectly acceptable.
They don't care.
Money.
Not money, not that they don't care.
They just wanted to mass manufacture things as quickly as possible.
No. So how did the guys on the aircraft carriers and the submarines and the U.S. Navy not get exposed to large amounts of radiation? I mean, the primary way to do it is to walk away from it, but you can't. You're stuck on a boat. So what do? Hanukkah?
They were blocked from it.
How are they blocked from it?
Doors, lots of doors.
Made of,
Iron, or not iron, but lead.
and what else do they need?
Water.
Walls made out of, with water in the middle of them. That doesn't do anything. Doesn't help out the boat. It's just shielding. So what did that do to U.S. submarines?
Made them heavier.
It made them heavier. If you watch a movie or read the book called Hunt for Red October, the guy who wrote that book, he's probably got 20 books now. And he was actually brought in by the FBI to the Department of Defense to ask where he got all his information about nuclear submarines. Like, was somebody telling him something? And he actually had to go, he took him to his house and said, this is all my research that I just picked up from libraries. So it's all out there, but he had to go out and read it all and then coalesce it into. So if somebody releases a little bit of pseudo-classified information, it's not a big deal. But if that happens a lot in different places and somebody's able to coalesce all that information, they can learn an awful lot. And he learned enough that he wrote, without being in the Navy, he wrote a realistic interpretation of what it's like to be on a U.S. naval submarine. And in a part of the book, or the movie, or the book, either one, we realized that, well, let me back up one sec. You guys know there are two types of submarines?
No.
There's a boomer submarine and there's an alpha submarine. This one goes deep and hides. It's filled with nuclear warheads. This one is really fast and goes all over the place, and it's looking for the other country's boomer submarines.
Oh, I think that's what I think submarines, like, that's what I originally thought that's what they were. Just things, they're just boats that travel and look for stuff.
Well, half of them are hiding, and the other half of them are looking for the other ones that are hiding.
Okay.
So the Soviet Union's alpha submarines are substantially faster than the U.S. military's alpha submarines. And after what we just talked about, can you tell me why?
Because they weighed less.
They weighed less. So the Russian Navy was willing to sacrifice the health of their sailors in exchange for better performance. So it wasn't about speed of production. It wasn't about cost. It was literally about, this boat's a better boat because I don't have X number of tons of lead and water weighing it down. Pretty much all those guys that were in the nuclear navy in the Soviet Union, they all got cancer and died in their 40s and 50s. All right, where were we? Okay, let's talk about a couple of ways to detect radiation. there's a couple of easy ways. And these are instantaneous. These aren't like a film badge or a thin layer a thermoluminescent detector that get hit with radiation and then are red. This is something that's telling you what radiation is happening right now. And so one of them is a gas-filled radiation detector. That looks like one that we had on our boat. That we had one of these in each reactor room, and we would use them for drills and periodically turn them on just for the heck of it. But it's we never needed it for anything. So what we have on the right-hand side is a graphical representation, and this piece right here, this is about the size of a male thigh for a man that's 160 pounds. That's how big this thing is. So it's actually bigger than it actually looks. Okay, this
I
is
thought it was like the size of a camera.
this is specifically this big to be the size of a man's thigh, because this is telling the man how much radiation he's specifically going to be exposed to. All right. All right. So what happens is inside this can, the can is filled. I mean, it's usually filled with argon gas. So what do you know about argon gas?
It's not reactive.
It's not reactive, but it's not the least reactive of the noble gases. We okay with that? So it's not going to chemically react unless something weird happens. And it's not going to hold on to its electrons as tightly as neon and helium does. So if I'm an argon just floating around inside of here, and some gamma radiation comes through this, or a neutron comes through this and smacks into me, I'm going to lose an electron. That electron comes off and my argon becomes positive. All right? And this is, billionth of a second kind of stuff. This wire right here in the middle is the positive side of a battery. And it's 2,000 volts of electricity. Okay? Which means the other side, and 2,000 positive, the other side is 2,000 volts negative, the anode side of the battery. We okay with that now? So tell me what this electron here does. It gets knocked off the argon. Under normal circumstances, it would find the argon again and reattach itself. But what would stop the electron from going right back to the argon? That's 2,000 volts of positive electricity. So it sees that and it goes into that wire. Well, this is an electron. So it went into a metal wire, which is conductive. So the electron goes through the wire, goes through the battery, goes through the counting mechanism, and then ends up at the exterior of the can. What is waiting for it?
The positive argon.
The positive argon ion, and then these two go back to where they were before, which was just argon atom. And then if there's more radiation, then the whole process happens again. So if there's enough radiation to have this occur, the argon atom keeps losing an electron and reacquiring it, and each time that happens, the electron gets counted. Does that make sense? So this is called a gas-filled ionizing radiation detector, and this one is for high energy stuff, gammas and neutrons. It doesn't work for the other radiation sources. Okay? And this one's pretty portable. I couldn't find a picture of the other one, so you're going to get a typical horrible drawing.
Amazing.
Do you guys know what Mylar is?
Isn't it like a film?
Yep. You know specifically what it is?
No, but it sounds super familiar.
Anybody?
I know that you can put it on glass to make really cheap one-way mirrors.
Okay. Anything else?
That's weird.
The balloons that are shiny, the metallic-y ones, those are made out of Mylar.
Okay.
Can you see through those balloons? Never.
No.
Never.
Oh, like the ones that are foil looking?
Yep, that's Mylar.
Okay.
There's no metal there.
So what is it?
It's just a polymer. I actually don't know what the formula is, but it's just like a type of plastic.
Okay. Just shiny plastic.
Yep. Do you remember when we showed the crux tube where Thomson figured out that an electron comes off of the atom? It was that green thing. It
Oh,
was like
yeah,
a
like
light.
the
It
light.
shot a green ray across it, and then you could use the
Yeah.
magnet to move it. So
Ghosts.
the reason, yeah, to talk to ghosts. The reason that paint turned green was because it was painted with a certain type of chemical that when it got hit with electrons, it turned into light. So this stuff on the inside of this, let me back up one sec. So the one we're talking about now is called the scintillation detector. Does anyone know what that word means?
Insulation.
Scintillation. In a chemistry sense, it just means a light-producing substance. So what happens is radiation, and it doesn't matter what radiation it is. This could be gamma, this could be beta, this could be alpha, or this could be neutrons. When any of these different types of radiation, they can go through the mylar. But visible light cannot go through the mylar. So in essence, this yellow stuff that I have here is sort of like glow-in-the-dark paint. And it's not going to glow in the dark. It's not going to be exposed to visible light to cause it to glow. It's constantly in the dark. So the only thing that can make it through the radiation or through the mylar is radiation. So when any of these guys run into this, the electrons in here get excited, and what do?
Emit light.
They emit light. The interesting thing about this is it doesn't matter what the radiation source is, it produces the same color light, it just changes the intensity. So this can't detect if you're being exposed to alpha, beta, gamma, or neutrons. It's just going to tell you you have radiation or you're being exposed to radiation. We use this detector after we came out of the reactor room. We had this thing that kind of looked like a detachable shower head. And then we would pass it over our skin at 2 centimeters per second and waited for the scintillation detector to tell us if anything was coming off of us. Okay, so the part I don't have on here is this is a light sensor. This light sensor can detect the light that's come off of the glow-in-the-dark paint. And it can detect just that one frequency of light, and that's all it can do. And when it does that, the light detector is like, oh, great. And it sends a signal down the wire saying, okay, we got hit by something. There's some exposure here. Everybody okay with that?
So would this, if you're using it for scanning a person, would this only effectively work for alpha and beta particles?
No, it works for everything. Oh, well, no, because if you're asking about gamma and neutrons, if that person had uranium on them, they could have alpha particles, beta particles, gamma, and neutrons coming out of the uranium. So what we use this for is to determine if the person was contaminated. Like they touched something and somehow they got it on them.
Okay.
There was a horrible case of a family in Mexico. They all died a horrible type of cancer within a week because it was like a grade school daughter was really just looking through a landfill for stuff. And she came across this rock that just glowed on its own. So she brought it home and showed her whole family. Extended family came over, grandparents, aunts and uncles, cousins, and everybody looked at it and held it and was like, oh, this is totally cool. It turned out that it was a used X-ray machine's cesium sample. So when they're like, you're going to get an X-ray now, and the person steps behind the curtain that's made out of lead, and then you hear the beep and it turns on, the thing that opens up, when the aperture opens up, it exposes or it allows the radiation coming from the cesium to run into you. and that's the X-ray that happens. Now this little girl is walking around with this, and then her whole family, and then it's just in the house. So imagine you're on the X-ray machine, and they turn it on, and they leave it on. They walk away for days. So all of these people died. And when they finally realized what was going on, all of the people in the neighborhood had to go through a process where they were checked to see if any of that cesium came off on their hands or clothes. So nobody was allowed to leave the neighborhood until they had the scintillation detector passed over them. So first off, the coolest part about this is it can detect any of the radiation, and the second coolest part about it is the scientific community that worked for the Department of Defense figured out a way to detect a particular wavelength of light. So why is that cool?
Can you use that to detect if it's retooled any particular frequency of light?
Yeah, what are you looking at on my screen?
Your phone camera?
Yeah. This camera right here,
Your digital camera.
oops. Sharing the wrong screen. The digital camera on your phone, that right there, that's the first one. That is the first detector of light, electronic light. So, sorry, electronic detector of light. So, does anybody besides Sheen know what this thing is?
The DARPA?
Yeah.
No?
Anybody? No? What is it, Sheen?
It's the Department of it's for research and
Department of Advanced Research. I thought you had it. Sorry, I was just giving you the advanced. Projects Administration. So, what is it though, Sheen?
they produce so many neat gadgets, like self-flying drones. Just like, oh man, I wanna see. It's just beautiful. There's so much cool stuff going on there.
So the DARPA organization doesn't build anything at all.
They just do research.
They don't really do much of anything other than give money to people. So they say, all right, this is what we want to happen. We have a bunch of cash and we will give it to whomever shows up with an idea that answers our question or accomplishes this goal. So my best example of this is about 12 years ago, they had $1 million prize to have a car drive itself with no outside input from Las Vegas, Nevada to Henderson, Nevada. It had to go through a particular obstacle course, which means they went through sections of the Nevada desert where there were rocks and crevasses and whatnot that had to go around. Does anybody know who won that $1 million?
Tesla?
Tesla wasn't even formed. Google.
Makes sense.
So since then, Google has been developing more and more vehicles that run on their own. So the technology that all of the self-driving cars come from, with the exception of a couple in Europe, all come from this initial Google technology. So in the time frame that they were supposed to, they had a car autonomously drive from one place to another place all by itself. Why would the army want that?
So that they don't have to put troops out?
Yeah. More than half of the troops that have died in Afghanistan since we've been there, this most recent time, since after 9/11, have died doing what?
Driving?
Just driving a truck around with like food in it, fuel, bullets. They don't want to have to transport anything and put anybody in harm's way. So now if the self-driving semi-truck that's driving through Afghanistan gets blown up by a roadside like a roadside bomb, then they're like, well, crap, we lost a truck and we lost a bunch of supplies, but no people died.
We didn't lose a human.
Right. So that's the goal, to not have any humans. And the predecessor to DARPA funded this research for a scintillation detector. The US Navy said, hey, we want to be able to detect radiation, all types of radiation, with one device. So here's a bunch of money. Somebody come up with it. So I can't remember who it did. It could have been Caltech or MIT. One of those probably did it. And they got a bunch of money for it. And then they just, used that to build more cool stuff. What's the well, maybe the camera phone is probably, or the digital camera is probably the most useful. What do you think the second most useful thing is that DARPA's produced? Or caused to be produced? What do you use your phone for besides surfing the web?
Calculations, compasses, or not compasses. but
Compass, right there. How does it?
navigation.
How does the compass work?
I really don't know.
Doesn't it use GPS?
It just used information from satellites. So where did that technology come from? DARPA. DARPA. So DARPA funded people coming up with, hey, we want you guys to build satellites and a device on the ground, and the satellite will tell us exactly where we are. So we've had GPS for a lot longer than the public has had access to it. So initially, there was no access to the GPS network. And then they decided to make some money off of it. So they sold it to different companies like Garmin and whatnot, and they put it on like these tracking devices, so you can walk through and like see where you're hunting or you're hiking and whatnot. But they only allowed the sensitivity to be within 100 feet. And then they released it to full GPS about 15 years ago, where it would be as accurate as possible, which is within a meter of the actual spot that you are. So think about that for a second. There's a satellite 500 miles above your head, and it's telling you within 1 meter of the location where you are or where you want to be. Unless you're on AT&T, then it'll tell you you're in Washington when you're in Parkdale. Okay, so I mean, the military is not always bad. Like sometimes they produce cool stuff. Does anybody know what the coolest thing that Napoleon's army created? Canning. He said, I want to go to Russia and kill people, but I can't carry all this food, or the food will go bad by the time I get there. So I want somebody to figure out a way for me to be able to preserve this food and walk all the way to Russia. And somebody did. And somebody won a bunch of money. And then he sold them the formula, and they started canning food and then put everything in wagons and then went to Russia to try to kill people. But they just left and burned everything before they got there. So can't get those Russian guys. Army autonomous weapons of the future. Okay. My brother just sent me something about a naval vessel shooting a drone down from 150 miles away with a laser. And my response was, I don't care about a drone. I want to know about the Hellfire missile the drone carries. Can it hit the missile? Because the missile flies like 10 times faster than the drone and is probably 10 times smaller.
In the book, he talks about that, and like, oh my god, it's beautiful.
All right. So,
Also, don't the Navy use chemical lasers, not electronic?
yeah. Well, I mean, they're powered by electricity, but yeah. I want to see the railgun actually hit something. I haven't actually I've seen the boat, I just haven't seen it fire. Okay, so, all right, those are the two types of radiation detectors. We have a scintillation detector, and we've got this gas-filled radiation detector. Okay, next thing we're going to talk about is half-life. Do you guys know the crux of half-life?
Gordon Freeman, and like opens a portal to like the Zen universe, fights aliens with a crowbar.
Um, is that a first-person shooter?
Really old, but yeah.
Is it like Counter-Strike?
It was produced by Valve.
It's made by the same people.
Yeah, same people.
Is it bad? You guys are laughing like it's bad. No?
No, it's good and something
Really
new
good.
called Half-Life Alex for VR. So it's on everyone's
It's
mind.
just
Good,
really
good thing
really
David
good.
can't count to 3.
Yeah.
Like Halo good?
It's a classic.
It's up there, not gonna
It,
lie.
it uses a lot of, it has like a physics engine, and it has like a gun where you can like push things around and like shoot razor blades at like aliens.
We're getting off topic.
Wild Blades and Half-Life.
Okay, does anybody know what Half-Life means?
It's the amount of time it takes for a sample to be decay into like something else, like half of it left.
Okay, so it's important that we understand that I have a time period that I start the clock at. And then if I've allowed the half-life time to go by, then I have half of what I've got. So let's say that the half-life for some object is 1 minute. After 1 minute, if I had 10 grams of it, I've got 5 grams of it. Now what happens if I wait another minute? Is it all gone?
No.
Now I've only got half of what I started with. So the clock restarts each time I want to determine how much time it's going to take. So how long is it going to take for all of it to go away? The answer is usually like 6 half-lives. So you end up doing something like this. Oh, wrong color.
If you're constantly
I know. It's a philosophical. At some point, the last one's going to go. Okay.
okay.
So if I've got this much at the starting point, if the first half-life goes, I've got half of what I started with, right? And then the next time I've got half of that. And then the next time I've got half of that. And then the next time I've got half of that. Eventually this curve looks like this, right? All right. Obviously not that.
There's like a weird bump in it. Someone added some more chemicals in it.
So it's so close to the x-axis that you can't tell, right? So it's usually after about 6 half-lives that either you cannot detect the source anymore because the background radiation is greater than the source that you're looking at, or it literally has completely used itself up. So this protactinium-234 has a half-life of 72 seconds. So if I start with 500 grams, time equals 0. I wait 72 seconds. I half of that is 250. So on the mass side of this chart, I just keep dividing by 2 because it's half-life. And on the time side of the chart, what do?
You just keep subtracting the time.
Do you see any subtraction there?
Time. Oh, you're adding time. Sorry.
What am I adding?
You're just multiplying it by 2, I guess.
Nope.
You're adding 72 seconds.
I'm adding 1 half-life every time, and in this case, it's 72 seconds. So that's why it doubles for the next one. But then the third half-life doesn't double. It goes from 144 to 216, which is just 72 more. So you just keep adding the half-life to the time side, and you keep cutting the mass side in half. So this says, how long is it going to take to decay to 10 grams left? So what's the answer? This is the answer. Okay? So you should be able to get this with relative ease. The in-between. It's after this time period, but definitely before that time period. And you cannot tell me it's probably around 395. Forget about it. You can't tell me that. You can only tell me that it's in between 360 and 432. Okay, so what if I wanted it to be more accurate? Then I got to use this equation right here. This one. So this equation is negative, and then whatever the half-life value is, divided by the natural log of 2, not the base 10 of 2, but the natural log of 2. And then the natural log of the original concentration, the original number of moles, in the denominator of the current mass, or number of moles, however you want to do it. Okay, so there's my half-life, 72 seconds. Natural log of 2 is just something you plug into the calculator. 10 grams is how much I want when it's finished. and 500 grams is what I started with. So this is going to take 406.35 seconds to get to that 10 grams. You okay with that? So you want to be able to do this calculation if I'm talking about something like, oh, I don't know, this is an impurity that is found in steel, cobalt is, or in iron. And when you turn it into steel, if I'm going to make this into something for a nuclear power plant, I can't have any cobalt-60 around. So I want you to find cobalt on your periodic table.
Okay.
I want you to flip over to the radiation side.
Oh god. How it's upside down.
It's okay. I want you to look at the second. So on the right hand side, there's a bunch of numbers. Look at the second one.
3.5 years.
So the half-life for cobalt, and the cobalt isotope that we're talking about is written right below it. It's cobalt-60. That cobalt-60's half-life is 5.3 years. So if I accidentally irradiated some iron and created radioactive cobalt-60, how long do I have to wait for the cobalt-60 to stop decaying?
3.5 years.
That will get me to half of it.
Oh, that's the half-life?
That's the 3.5 years is the half-life. So if I wait 6 or so half-lives, I will be pretty good. So how long would I have to wait on this?
6 times 3. Okay, Google. 6 times 3.5.
It's 5.3. Nice try though.
It's
Yeah, that's wrong because it's 5.3.
oh yeah. It's
Dyslexia.
upside down.
Ouch.
No, it's not dyslexia. It's upside down. So I had trouble.
Okay. But we all get the point, right? It's more than 30 years. So when they decommission a nuclear power plant, since they can't get rid of all the cobalt in the steel, those parks usually sit someplace for 30 years to make sure that there's no intrinsic cobalt-60 left over. We good with that?
Yeah.
What if I wanted to do it a different way?
And you do you.
What if I wanted to, I know what I'm starting with, and I know how long I want to wait, and I want to know how much stuff is going to be left. So I've got, say, I don't know, 500 grams, and I want to wait for 50 years. I want to know how much stuff is left. How do I use this equation?
Algebra, you just fill in whatever time you want with t.
Okay, that's fine, but how are you going to algebraically do this? I'm going to grab this, move the, oh, come on. Really? You're not going to let me move that. Okay. Grab a little copy of this guy. Go back over to this untitled page. Paste it in here. Hey, where'd it go? All right. Put it right here. Okay, so how do I do the algebra? What do you want to do first?
So you said you already had a set amount of time, right?
Yeah, I am looking for, I want to solve for this.
So then we put in our time amount.
No, I want this equation solved.
Divide both sides by ln and over n.
No. That won't help me at all.
Just like, would you multiply by the inverse of the fraction?
Okay, sure. So first thing I'll do is I'll multiply by -1, right? So that gets rid of that negative sign and puts the negative sign on the other. We good with that? Everybody okay with the easy start I gave you?
Mhm.
And then we'll keep doing what Kalina said. So I'm going to divide this side by half-life, right? I'm going to divide this side by half-life, and the half-life cancels out. I'm going to multiply this side by the natural log of 2, and that cancels that out, and I'm going to multiply this side by the natural log of 2, And then when I do that, I'm going to end up with the natural log of n divided by NO equals natural log of 2 times time divided by half-life, and all of this is negative. So here's the part that most people don't understand how to move. How do I get the ln to the right side?
Bring it to the power of B.
Bring it to the power of e. So if you look on your calculator, there should be an ln and then there should be an e. Or it might say e to the x. It's not this e or this e or this e. It's none of those things. It's going to be a lowercase e. And so lowercase e and ln are the opposites of each other. So if I take the e of this side, the ln disappears. But I have to take all of this, and it is now the exponent of an e. Okay, so let's write this again. So now what I have is n divided by NO equals e with the exponent of negative natural log of 2 times time divided by half-life. And then I multiply this side by NO, multiply this side by NO, and I end up with n is equal to well, I'll go NO times e negative natural log of 2 times time divided by half-life. All right with that?
So is that the equation where we would use then?
If you were asked to answer it like this, then yeah. This would also work if I wanted to know what the original concentration was, right? So let's say I find an object and I know how long it's been sitting around, and I know what the current radiation level is. I can figure out what the old radiation level was. So what did we say? We had 500 grams. What else did we say? We didn't say anything else, did we? Let's do that cobalt 60. So I know that the half-life is 5.3 years. And let's say that we waited around for 25 years. Okay, so 500 grams times E, natural log of 2 times 25 years, divided by 5.3 years. Years are gone. Let's see what we get. 500 times... On a TI-89, it's Diamond X negative natural log of 2 times 25 divided by 5.3 close parentheses. I'm going to have 19.0 grams remaining. We good with this? So just some algebra that you may or may not have used before.
Mm-hmm.
So how do we use this to date things? Well, if I know about how much stuff should be there, and I check to see how much stuff is there, and then I use the half-life, I can backdate to figure out how old the thing is. So how do we know how old, like, a wooden spoon is that somebody pulls out of the ground from an anthropology dig?
Can we take like pieces of it to analyze?
You don't even need to. You can just
Under a
take
microscope?
the whole spoon and put it in a detector.
What kind of detector?
Well, what would you be detecting?
Radiation?
Yep.
Or
Yep.
okay.
Half-life
Why would
of
this?
carbon?
Half-life of carbon. I'd be checking for the half-life of carbon. Why? Because the spoon's made out of wood, and I know that there's carbohydrates in there, so I know there's carbon in there. So
So
if I check for the amount of radiation that's the amount of carbon-14 that is inside that spoon, I know how much is in a live tree, And so that will tell me how old that spoon is, how old that wood is. Does that make sense?
Yeah. So, do half-lives then not just work for radiation? Can they also just work for elements or isotopes?
I don't understand your question because we're
We're talking about
specifically
carbon.
talking about a nuclear reaction that happens inside of an atom.
Okay.
All of the half-life stuff is a nucleus undergoing a decay and transmuting into a different nucleus.
Okay.
So carbon 14's dating, if you find it, it shows on the periodic table as 5,730 years. So how old can stuff be for us to still carbon date?
Old.
Let's say you find hair from a frozen skeleton in the Arctic, because we are doing that now. As the Arctic thaws, we're finding these frozen dead bodies and wondering how old they are. So we take the hair and we check it. So how old could the body be and still be useful as far as carbon 14 dating goes?
Thousands of years old.
Biology that it was like 65,000 to 55,000 years.
It's closer to 40,000 years.
It was a really weird answer. It was different everywhere you looked.
It really is, because some people think they can more accurately detect it. And I don't doubt that there are ways to do it, but do you know how we detected the neutrino? By we, I mean humans. Anybody read that research?
No.
There's a well that's like, I don't know, I forget what it was, something stupid, like 1.5 kilometers deep. And they took all of the equipment down 1.5 kilometers, and it was in this, and it was in water. And they left this thing buried, sunken below this water for more than a year. And the reason they did that is because the radiation is being blocked by the water, and no solar radiation can get access to it. So they were detecting things that aren't blocked by mass. So the neutrino doesn't interact with mass, so they detected it in that way. So if I took the spoon and I took it to that place and checked its carbon dating, it could maybe be 60,000 years, but that's not something most people are able to do, don't have access to this place. So if I'm just doing this in a lab on the surface, 40,000 years is about it. So why am I saying 40,000 years? Because if I take 5,730 years and multiply it by 6, I get around 40,000 years. So the problem is the radiation that we just have on the surface of the planet, coming out of your own body, coming out of if I'm doing this test, there's probably a lot of plastic around, so there's carbon around. And so those things have carbon 14 in them, and they're decaying. So there's just radiation around. So the background radiation causes noise, and I won't be able to tell at lower levels what the radiation is. So I suppose you could do 60 if you had an incredibly shielded environment, but 40 is about it. Well, how do we know the age of a Tyrannosaurus rex? Because it's considerably older than 40,000 years.
What's potassium?
We use potassium. So we move on to other types of radioactive decay. So this one right here, the uranium to lead one, that's not super useful when I'm trying to date a dinosaur. Why?
Because
They typically are not radioactive dinosaurs, right? I mean, unless we're talking about Godzilla, there's no radioactivity. So these uraniums aren't useful. Rubidium is a decay product of uranium, so that one isn't helpful. Samarium isn't something that's typically found on this planet, so that's not helpful. But potassium, living organisms have potassium in them. So the potassium half-life is what? It's 1.25 trillion years. So I can determine how old these things are, but the problem with using this kind of half-life, I mean, why don't I just use the potassium one for the spoon?
Accuracy.
The accuracy is when it's plus or minus 100,000 years on a dinosaur, everyone's like, yeah, that's close enough. But if I said plus or minus on a spoon and my answer was plus or minus 100,000 years, and you're like, humans haven't even been here for 100,000 years, so That's a useless calculation or useless determination. So we'll only use it on really old stuff. The Sumerian one and going into neodymium, that one is super useful to determine just how many damn times we've been pummeled by meteors. Because the Sumerian isn't typically found on Earth, so that means it's come from an outside celestial body. So we either got hit by a comet or a meteor. And so we'll find these things around. And interestingly, when we find them, what shape do we find them in?
Good shape.
A circle. So I find some here, and then if I start excavating around, I'm going to find, oh, there's some here and some here. We'll just follow it around. And why? Because something got hit right there. Let's do... all right, I can't spell Arizona evidently, but it's okay. What does this look like? It's a big crater. Great. Anybody have any idea what might have caused said crater?
A meteor.
Well, for at least 100 years, people said that it was some sort of geological, like a steam explosion, some kind of almost a volcanic-y kind of thing. And they rolled with that for a long time. And then there was a guy who was a geologist who was enamored with this crater and thought, this looked exactly like every damn crater he's ever looked at on the moon. So how could this one be any different? Because they know there's no geological activity on the moon. So what he did is he inspected the hell out of it during grad school. And what he did is he found this. This mineral is called cosite. And cosite is produced under a specific set of circumstances where the temperature and pressure, I mean, read that first sentence.
Gigapascal?
2.3 gigapascals. So how do you get a gigapascal on the surface of the Earth? Or on the Earth at all? The center of the Earth is nowhere near a gigapascal as far as pressure goes. So what had to happen?
Had a pummel.
Something hit us hard and produced a bunch of heat. So you can create this mineral at 2.3 gigapascals and 700 degrees Celsius. So he said, I find this cosite there. You cannot tell me that this came flying, pluming out of the ground. It doesn't exist on Earth. They can find it in moon rocks. Does it make sense? Moon's been utterly pummeled. So then after he did this, he actually was slated to go to the moon. And then he got measles. And his alternate had to go. Yeah, it was like biggest disappointment of his life. So then he had a side job of finding craters. Governments would hire him and say, is this a crater? And then he would go, and the best story that I read from him is this Austrian town asked him to come and inspect to see if it kind of looks from the air that their entire town is built inside of a crater. And he took a cab there, he gets out, and they drop him off right in front of this giant Lutheran church. And he's like, why is the surface of that church like diamondy shiny? And he walks up and he sees cosite buried in the rock that they built the church out of. So immediately he's like, yes, your entire church is built out of cosite, which are rocks that probably came in a circle from exterior of this town. And that's true. So he went out to the exterior of the town and found rocks that had this cosite in it. So this guy was basically the person you'd go to find out if meteors had hit the Earth.
Cool. He sounds like a cool dude.
He is a cool dude.
What was
He,
his name?
Eugene Shoemaker.
I'm sorry, what was he immediately like? My internet just kind of crapped out.
He is the person that you would contact if you wanted to know if some kind of geological formation in your town, state, country was caused by a meteor. So he's the one that determined that Can I copy this straight away? Dig that. That's a meteor impact.
Really?
Yeah.
I mean, it makes sense. It's like circular.
How do you know? Cosite, 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 above water, underwater, cosite. And this impact correlates with death of.
Dinosaurs.
So they half-life the cosite, and they find out the cosite has impurities for the samarium and neodymium in it. And then they realize, oh, this happened then. When did those dinosaurs die? Oh, right there. So anybody who says that the dinosaurs were killed by anything except a meteor impact, they're just wrong.
People say that dinosaurs. I didn't know that there was like a.
There's theories that volcanoes
Oh.
caused it.
And the Great Flood.
Oh yeah, the Christians. I forgot about them.
Rob, have you seen the core samples they took from the under the Gulf of Mexico?
Nope.
They're this massive multicolored aggregate of all kinds of different rocks. With oh man, it's something to see.
Okay, I'll look that up. The last thing about Shoemaker is in his backyard with a telescope about the size of 5 Home Depot 5-gallon buckets put together. He found, actually his wife did, totally by chance. Him, his wife, and their friend were over having a barbecue one night when it was really clear, and they were just scanning the sky for the heck of it, and they wanted to look at Jupiter's moon. And after they looked at Jupiter's moon, they went to go over look at Saturn, and on the way over, something caught their eye, like a glint in the sky where stars shouldn't have been. I mean, think about how amazing your star map is in your head to realize that the thing you just saw wasn't a star, it was out of place. So then they went back to it and they're like, holy cow, those are some kind of meteor or comet or something. And it was 4 of them in a row. Like it had broke, like something hit something and broke into pieces and was traveling into our solar system. And they did a quick calculation and realized that's going to hit Jupiter. And so they told NASA, and NASA told the rest of the world, they're like,
How
hey,
did they just tell NASA? Oh yeah, he was
He's-
back.
because he was, going to go to the moon. So they tell NASA, and actually, you can tell NASA that you've seen a planetoid or a meteor. They actually have a way to tell. There was like a 15-year-old kid last month that found two
Nice, good.
two unknown objects in our solar system outside of the asteroid belt. So so they tell the world, hey, these are going to hit Jupiter, and no one had ever heard of any. We wouldn't fully believe the idea that a planet with an atmosphere could get hit by anything, because we get hit by meteors all the time, but they don't make it to the surface, right? Shooting stars. So they were under the impression, a lot of people were like, no, God would never do that to us. Well, God doesn't care. So let's see this happen. And there's video footage of these meteors running into the surface of Jupiter and causing explosions that make Hiroshima and Nagasaki look like firecrackers.
That's crazy.
So we are 100% sure that meteors impact celestial bodies because we've seen it. All right, so we're going to talk a little bit about this and then call it a day. So
Didn't we already talk about that image that you just showed us?
this?
No. Well, it's going really slow. I can't.
Okay, we're going to talk about this. So
Yes.
when something's radioactive and it undergoes a decay, that doesn't necessarily mean that it's no longer radioactive. All right? And so when that happens, it's called the decay series. So the uranium atom doesn't decay straight into a non-radioactive substance. in the case of uranium-238, which is most of the uranium on the planet, uranium-238 turns into thorium. And that uranium-238, it takes 4.5 billion years for the uranium to turn in, for half of the uranium to turn into thorium. The Earth is 4.5 billion years old. So half the uranium that the Earth had is now been decayed into something else. So then it only takes 24 days for the thorium to turn into that protactinium, and it only takes a minute for that stuff to turn back into uranium. How did it turn back into uranium?
Different neutron numbers.
No, that has a different neutron number, but it's still the same 92 protons. This is an alpha decay, right? So this causes the proton number to go down 2. This is a beta, which causes the proton number to go up 1. This is a beta, which causes the proton number to go up 1. So we're back up to uranium. But now we're at uranium-234. And then it undergoes an alpha decay, an alpha decay, an alpha decay, an alpha decay. And then we get to this polonium, which either can do a beta or an alpha, and then it'll do an alpha followed by a beta, end up back at the same spot. And it can split and go either direction, but then they both end up at the same spot. And then it can go to bismuth, and that can split, but then they both all end up at the same spot. So lead-206, tell me about the lead-206 on the planet.
Constantly increasing.
Lead-206 atoms on the planet are constantly increasing because you can't stop uranium decay. So it's constantly turning into the final stable atom, which is lead-206.
Isn't this one of our labs? Because I just kind of like did it today.
This is one of your
I was
labs.
learning it, so I didn't know we were going to go over this.
Yep. So there's first off, this is a billion, or this number up here, billion. We okay with that? Days, minutes, thousands, 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 days, minutes, seconds, minutes, days, minutes. So which one of these things matters? Only that one, right? I know 25,000 years is a long time, but it's nothing compared to 4.5 billion years. Okay? So when we're talking about how long it takes uranium to get down to lead, we're basically talking about 4.5 billion years. All right, so that's one thing. The other thing is just to notice that it switches between alpha decay and beta decay. And then the final thing is we need to play some Sesame Street. Which one of these is not like the other? And I'm not talking about the lead-206 that's stable. One of the substances in this decay is fundamentally different than the other substances.
Is it the radon? Or
18. What is that? Actinium? No, it's
Sorry, I heard something weird. I had to go check. I heard it. The answer is radon. Why is radon weird?
Isn't it a gas?
It's a gas. All the rest of these things are solids. So this is happening in the soil. Okay? But I don't care about this thing right here. Why? It's a solid in the soil. It doesn't have access to me. But this thing, it's not just any gas. Because if this was hydrogen gas, I wouldn't care about it either. Because it would be super chemically reactive and react with the soil on the way out. This thing is a noble gas, meaning the chemistry is that it doesn't chemically react. So it's in the soil and it literally just starts seeping out of the soil. So why is that a problem?
That's a radioactive gas.
That's a radioactive gas. Yep. You can't smell it. You can't taste it. It's just a radioactive gas that just happens to be coming out of your soil. So is that a problem?
Yeah.
When would it be a problem?
When it becomes uranium, right?
No.
Because it goes up and up.
No, it never turns back into uranium.
Would you have a uranium deposit? Or
Like poor ventilation.
Poor ventilation for what?
When
Mines?
does it become radioactive dust?
A basement. It's not a dust. This is a gas. Kalina's got it. It's a basement. What happens if your basement is poorly ventilated? Which, I mean, think about basements. There aren't any windows usually. So the gases that seep up from the soil through the concrete. That's funny. Kalina, are you in a basement?
I am right now.
Where are you in a basement? What city?
Hood River.
You're okay.
Hopefully.
You're okay. If
There's
you
no
were
windows down here.
if you're in a basement in Parkdale, you wouldn't be okay unless you've done some mitigation. So when we built this house, we had to install a fan that went to underneath the house. So there's a like 2 to 4 foot crawl space depending on where you are under the house, and there's literally a pipe that goes in there with a fan that runs 24/7 that pulls air out of the crawl space and distributes it up to the upper atmosphere. So if the reason it's a problem is if you're in that poorly ventilated basement and you breathe in radon gas, what could happen while it's inside your lungs?
Answer.
It can decay, alpha decay, and now it's an alpha particle and it's inside of you. That's the only time alpha can hurt you, right?
Oh, right. Whenever you ingest it.
So you just ingested it through inhalation, and then it decays into your super soft, susceptible air sacs that get lung cancer.
Oh no.
When radon gas does decay, does it become a radioactive dust though? And believe
Yeah, polonium would stay.
Yeah.
You'd end up with. So not only do you get the alpha decay here from the radon, now you're stuck with the polonium, which will either beta or alpha decay, which will then beta or alpha decay, which will then beta or alpha, which will then alpha or beta, which will beta alpha or alpha beta. So how many times did this thing hit you? 1, 2, 3, 4 alpha decays. 1, 2, 3, 4 beta decays.
And that's just like one of it,
That's
right?
one atom decaying inside of your lungs. Yeah.
Yeah, so 8 times.
Yeah.
The biggest number you can think of.
Plus, it's an alpha particle, right? So you multiply that quality factor by 20. It's like a truck inside your lungs. It hits something, bounces off of it, ionizes it, and hits the next thing. So the reason it's so dangerous is it literally comes out and wrecks 20 different cells. The beta particle wrecks one cell. Okay. We will. I still have something more to say about this, but I'll start it in the homework, and then we'll finish up with these last few pages on Tuesday, and then move into the organic stuff.
Okay. Thank you.
All right.
See you on Tuesday.
I will be here.
Bye.
See ya.